Okay, so welcome to another series of videos. So now these, as promised, so if you remember when we went over one-dimensional kinematics, and in particular the kinematic equations, I didn't actually derive those in class. I promised to actually do some videos to show how they're derived, so that's what I'm going to do now. So remember, we're looking at one-dimensional kinematics. Okay, so there's one very important assumption that we're going to make when we do this. So, well, there's actually a few assumptions. So, one of the assumptions is we're going to assume that our initial times are always zero. So, and that's actually not such a crazy thing to do. Remember, this is sort of where we start our stopwatch. So, and we can always define how we measure things so that our initial time is zero, and when we do that, it actually just gets a little bit easier because then remember delta t, which is t minus t initial, but if t initial is zero, then we can delta t and t are exactly the same thing. Okay, so now one other assumption that I'm going to make. For now, I'm going to also assume that our initial position is also zero. So x0 is equal to 0, which has the same effect. So if we're interested in a displacement delta x, which is x final minus x initial, but if x initial is 0, then delta x is the same thing as x. Just makes the notation a little bit easier. Now, here's the big one. Now, the most important assumption that we're going to make is we're going to assume that the acceleration is constant. Now, this is important because if you have a constant acceleration, then something rather interesting happens. So for constant acceleration, it's always going to be true that your average acceleration is exactly the same thing as the instantaneous acceleration. Which makes sense if you think about it, right? So constant acceleration just means the acceleration isn't changing. So it's some particular value that doesn't change. So then whether you talk about the average or whether you talk about the instantaneous, they're both going to be exactly the same thing. Now, this actually is all we need to derive the first of our kinematic equations. So the first kinematic equation, remember, we just use our definition for average acceleration. So average acceleration is change in velocity over time, which is v minus v initial over t minus t initial, but remember we decided we're going to let t initial equal 0. Now, here's the key point. Average acceleration is going to be exactly the same as instantaneous acceleration, as long as acceleration is constant. So, I can use this for the instantaneous acceleration, so I don't have to do any pesky limits or derivatives or anything crazy like that. So now let me just rearrange a little bit. So multiply both sides by a t. That gives me v minus v initial equals at. I'm going to add a v initial to each side. So that gives me v equals v initial plus at. So that is kinematic equation number 1.